Hello and welcome. My name is Alex, founder and director of MPSI Technologies. This is the first episode of our brand new The Whiznium Developer Experience format. Whiznium is an innovative open source development solution for embedded software. We decided to start this format because we thought that it is the best way to communicate you as an embedded developer, why it could be of advantage for you to choose the Whiznium Developer Experience for your very own and diverse projects. This series features 6 episodes, and this is the first one of it. It's called Why Whiznium? Let the Laser Scanner Do the Talking. Let me explain the title. This presentation has 2 parts, in the first of which I will pinpoint current challenges in embedded software development and how Whiznium helps solving them. In part 2, I will work with our starter kit, a tabletop 3D laser scanner, to exemplify a number of advantages when developing with Whiznium. Over the past decade, it has become increasingly complicated for you as a software developer to construct high-quality software which can make good use of all the vast resources that are available in modern embedded systems. While embedded software design used to be limited to microcontroller programming for single-core processors in C and assembly language, with the advent of cheap, affordable single-board computers running embedded Linux and also programmable logic, the job of a software developer has become more and more demanding. At the same time, there are numerous programming patterns which are commonplace and which result in repetitive coding tasks. Those are related to, for example, databases, communication, web-based user interfaces, access rights management, communication between FPGA and host system, just to name a few. To avoid wasting valuable developer time with the Whiznium project, we decided to come up with a coherent approach which allows to have code for these features generated automatically. Our clear intent is and has always been that the machine does the repetitive stuff so you as a developer can focus on the detailed implementation of your specific application. So how does it work? Whiznium offers you to model the various aspects of your embedded system software in terms of model files. Out of these, it will generate high-quality, well-structured source code trees, which can be complemented with manual code. The source code trees are compile and synthesize ready from the first iteration onwards. We think that Whiznium differs from existing solutions in several aspects. We have 4 key points to make. First off, we cover vertically everything starting from state machines and pipelines, algorithms and FPGAs, and MCUs, but that's relatively new to Whiznium. Whiznium helps design multi-threaded applications running on embedded Linux computers, and finally also takes care of code for communication to the outside world, which can be web-based user interfaces, but also communication with M2M protocols such as OPC UA and DDS. Second, we generate source code trees which can be complemented manually. This is in contrast to wizard solutions. Once the model changes and Whiznium generates the next version of the source code tree, the manual changes are progressed into this next version. In addition, not only are no closed source libraries involved and no license fees due for the resulting code, but to ensure maximum independence for you or your company, also the Whiznium tool itself is open source. It can be extended to specific needs. Finally, I would like to stress that with Whiznium we are not offering a new programming language because we really think there are enough well-suited programming languages around. Early on in the project we settled on the most widespread languages. Whiznium generates VHDL and C code for the FPGA MCU level. For the embedded Linux software level it's mainly C++, and for the web-based user interface we use plain HTML5 and JavaScript. With this information, I would like to conclude the first part of this presentation. Now, let's move on to the second part. As we are offering a new tool, it is very important for us to make clear to any potential user what he or she can make out of it. Embedded software is not, as you know, in any way similar to apps or enterprise software, in that it only makes sense together with a nice piece of hardware that is to be controlled. For this reason, we decided to come up with an affordable starter kit, which should also be fun to work with and which can show almost all aspects which are covered by Whiznium. The device is a tabletop 3D laser scanner, looking like this. So, you have a turntable where you can place an object, and you have a camera and 2 line lasers which are directed at this object. Currently we offer the starter kit in 2 versions. One is based on Toradex's Apalis iMX6 single board computer. It's a quad-core running embedded Linux. And as here is MPSI we are big fans of programmable logic, we also have another version on offer, based on Digilent's Cora Z7, which uses Xilinx's low-cost Zinc 7010 device. Of course, we are always also monitoring very interesting developments in the industry, such as RISC-V, so be prepared for additional versions of the starter kit in future. But for this presentation, we will focus on the 2 mentioned boards. Now, starting with the embedded Linux solution here, let's get right to it. What we see here is the login screen of the web-based user interface, which already shows that we can have multiple languages and I can log in. It is possible to give fine-grained credentials as to which user can control which aspect of the embedded system. Here we are looking at the auto-generated navigation screen. All Whiznium projects include the database that can be extended freely beyond the standard tables for users and user rights management. In the past, we have rarely come across an application that cannot make use of some kind of organized data storage, and the corresponding user interface features come for free. For the 3D laser scanner application, we have objects organized into object groups which categorize the snapshots and files which will be acquired. Going into object groups, we see those which are currently stored in the database. And just for this demonstration, I will add one more object group underneath Office items, which is called cups. As in this demo we are planning to scan a Nescafe cup, I will add this as an object underneath the object group cups. Alright. Again, I should note that all the user interface you've seen so far is fully auto-generated by Whiznium based on the database model input. Now let's go to the actual acquisition part, which offers all the access to the hardware. It is organized within the live data card with 3 panels: calibration, 3D reconstruction, and system monitor. The monitoring feature is only here to illustrate the CPU load running the various algorithms, also compared to the FPGA-based solution. As for calibration, we can see here that we have a user interface that offers a camera view and overlays coming from the various algorithms. It is important to perform proper geometrical alignment, for which we supply a printed alignment mat on which turntable and camera can be placed accurately. This manual procedure had been done before. The resulting working distance can be read from the mat and adjusted here. So for our case, it is 22 centimeters. As for the camera preview, we can select the several mode. We can set the focus. And we can also change the exposure time in manual exposure mode until only the laser traces are visible in the image. I should have come from the other side here. So these are the laser traces which are relevant for object detection, and I make sure that in the image only those remain visible. To test whether the laser traces can be detected, I can switch on the algorithm here, and indeed we can clearly see the left-hand side laser as red trace and the right-hand side laser as green trace. We are now ready to acquire the 3D point cloud. During acquisition, the turntable will turn in angle increments which are specified here. We see up here that we are now monitoring in a sense. We are seeing the laser traces being identified, and we also see the resulting 3D point cloud take shape in this view. While the acquisition takes place, I would like to show you other options of how to communicate with the server besides the web-based user interface. Applications generated with the help of Whiznium out of the box have numerous options to communicate with the outside world. With the help of Matrican's OPC UA Flex SDK, which is a paid option catering to industrial automation users, it is possible to access all features of the project via an automatically set up OPC UA namespace. To show this, I switched over to the other screen where I can connect to the server like this. And once I'm connected, I will see the individual features of the detector cleanly organized into C++ classes or jobs in Whiznium, and I can, for example, monitor the rotation angles of the turntable here. So as we have specified 7.5 degrees angle increments, you can see the according movement live, also in the OPC UA namespace. We will get back to the concept of jobs and namespaces later in this presentation. Secondly, I would like to show access via industry standard DDS, which is provided by the paid option of Real-Time Innovations Connect suite. This feature should be of particular interest to robotics users. Right here, I have SPY tool, which, as the acquisition is running, continuously gives updates of the various state variables. Finally, I would like to show yet another quite straightforward option of communicating with the daemon within the embedded system. We can use the fact that all device features are accessible via a web-based user interface, and access takes place via project-specific XML over HTTPS communication. With any project, Whiznium delivers matching C++ and Java libraries which implement this communication as a remote API library if you want. Here I show a Java demo, which is built on top of the Starter Kit's Java API library. This is a fully custom Java user interface. Nevertheless, I log in the very same way that I had logged into the web-based user interface. After login, I can start the camera view. which admittedly during acquisition is very dark. But as we are through with it, I can go back to auto exposure and I will see the image. On the right hand side, I can access the database and select our object group and object, and finally the files which we have acquired. By now the acquisition of our point cloud has been completed, and as you can see here in the web browser, the cup object is clearly identifiable, including its handle, and it can be processed in open source tools like, for example, MeshLab into a solid body. Before finishing this episode, I would like to make some remarks on the FPGA-based starter kit version, which I also have here next to me on the table. So, the functionality is the same and the software is the same, only that the relevant imaging processing algorithms run within the programmable logic. In fact, compared to the embedded Linux version, the camera is now not wired up to the ARM processing cores via MIPI, but it's connected to the programmable logic with a digital parallel interface. When I log in, and look at the live data card, I see that things look pretty much the same as compared to the embedded Linux version. Only that in the system monitor I have just 2 cores available as compared to the 4 cores in the embedded Linux version. We will see that this is largely sufficient when much of the compute load is being performed with efficient pipelined FPGA algorithms. The one algorithm you're already familiar with is laser line detection. Another one is corner detection, which is intended for future use to automatically find the alignment of turntable with respect to camera. When I switch on the algorithm, it will find the edges of the checkerboard and it shows them as blue spots. All the calculations such as gradients are performed in a pipelined algorithm on FPGA. So as you see here, the CPU cores have very little to do, and even less when I switch off the preview. As I still have one more substantial Whiznium concept to show, I will launch an acquisition on the FPGA-based version and use the time it takes to introduce you to that point. So let me prepare this. This time it will be a cactus. And same procedure. I have to make sure that only the laser traces remain visible to the algorithm in the end, which I can validate by clicking on the trace button. This seems to need a bit more exposure. Okay, so I start this. And now have time to introduce you to the Whiznium concept of hierarchical job trees. Here we are looking at the command line of the embedded systems daemon. When I type at any time the command show jobs, it will display a dynamic hierarchical structure of objects at runtime. Here you see that there is one root job underneath which there are jobs for every session opened by a user or by a M2M client, such as the OPC UA session we had seen before. Under a session, there are UI jobs split into cards and panels. So for example, this, our live card, corresponds to this object on the server, and you will find one job or C++ class for every panel underneath. So while this organization already is very helpful for things like access rights management and state control, I would now like to highlight one of the advantages of the hierarchical job tree for hardware control jobs. On one hand, for any hardware aspect to be controlled, at any time it has to be clear which actor is in control. On the other hand, numerous actors may be interested in the output of these aspects. Take as an example the preview images from the camera. Whiznium solves this conflict by having a client-server option for hardware control jobs. For instance, here you see that there is one master job acquiring traces from the FPGA subsystem, and then in the point cloud job, this trace detection job is again listed, but this time as client. So this arrangement makes sure that only one job is in control, and the server job will pass its information or results to the client job, where they can be processed by, in this case, the point cloud super job. By now our Cactus acquisition has completed, so that somehow worked. And this concludes my presentation part 2 for this episode. I'm really glad you tuned in. I hope that you had some takeaways for your own projects. Thank you for your attention, and I hope that you will be back for one of our next episodes. If you have any questions or any requirement regarding the open source Whiznium developer tools, please feel free to reach out.